This is video number 17 from Digital-University. We're dealing with various topics in linear algebra. In this video, we want to show how to diagonalize a matrix, if indeed the particular matrix is diagonalizable. Before we do, let's just take a look at the results we had from our last video, number 16, where this was the matrix and this was its corresponding eigenvalues. It's a 3 by 3 matrix, and it has 3 distinct eigenvalues, and each eigenvalue had a corresponding eigenvector. And here they are, here, here, and then the eigenvector corresponding to eigenvalue minus 5 was this. Remember, when you have an eigenvector, if you multiply it by a constant, that is still an eigenvector of that particular matrix. So we could multiply through here by 3, and this would still be an eigenvector. So here, here, and here are 3 different eigenvectors that correspond to this matrix. What we want to point out is that these 3 eigenvectors are linearly independent. And whenever you have a matrix, whether it's a 2 by 2 or a 3 by 3 or an n by n, let's say just say in general an n by n matrix, if you get n distinct eigenvalues, then the corresponding eigenvectors are guaranteed to be linearly independent. In one of the future videos we might have a proof about that, how to prove that statement indeed is true. Right now we'll just take it and work with it because that's the background we need to diagonalize a matrix. Now when you have an n by n matrix though, all of its eigenvalues don't have to be distinct, in which case the corresponding eigenvectors, there might not be an n number of corresponding eigenvectors. That gets to be a little bit more complicated. We'll deal with that in future videos. So right now, this particular video, we're going to be dealing with, we have an n by n matrix, you have an n number of distinct eigenvalues, so that all the corresponding eigenvectors are linearly independent. And to show the process for diagonalization, we'll illustrate it for our 2 by 2 matrix. But the same process applies to a matrix of any size. So let's say that we had a matrix like this, a 2 by 2 matrix, and this matrix had 2 distinct eigenvalues. Therefore it has 2 distinct eigenvectors, and we'll call them x1 and x2, and each one of course will have 2 different components. So this can be 1a and 1b, and this would have components x2a and x2b. Well, with the components from these eigenvectors that correspond to this matrix here, we can make another matrix with these. So we started with a given matrix, we'll call it matrix A. We found 2 eigenvectors for it. Here they are in component form, and we're making another matrix with these eigenvectors. What happens if we multiply matrix A times this matrix? Like this. So this is just eigenvector 1, and this is eigenvector 2, and let's write this below. This is our original matrix A, and the matrix that we form from the eigenvectors of matrix A, in most textbooks they call this the S matrix. Now, if we multiply these two together, then of course all we're going to get is A times eigenvector 1 plus matrix A times eigenvector 2. But because this is an eigenvector, this would also be equal to lambda 1 times that eigenvector plus lambda 2 times this eigenvector. So what we have is matrix A times matrix S equals lambda 1 times the corresponding eigenvector plus lambda 2 times the corresponding eigenvector, where eigenvector 1 has these two components, eigenvector 2 has these two components. And this we can write like this. Times this diagonal matrix. So here we made a diagonal matrix. The diagonal elements are the eigenvalues of this matrix. And we multiply across, and down we'll have x1 times lambda 1. Across and down we'll have lambda 2 times x2. Now, these of course have this component here, so this is just, again, our S matrix, and this they call the D matrix, D standing for diagonal. So what we have is A times S equals S times the diagonal matrix. Well, now, again, matrix S, that's comprised of the eigenvectors of matrix A. And those eigenvectors are linearly independent. Therefore, matrix S is non-singular, so it has an inverse. So let's multiply both sides of the equation by its inverse. So now we have the inverse of S times matrix A times S will equal the inverse of S times matrix D. But this, of course, is just the identity matrix. And when you multiply any matrix by the identity matrix, you just get that matrix. So this is just equal to D, the diagonal matrix. So what this means is that you have a matrix, you found its eigenvectors, you use the components of those eigenvectors to form this S matrix, which is non-singular, find its inverse, then when you multiply these three matrices together, you get a diagonal matrix, whereby the diagonal elements here are the eigenvalues of this matrix. So, to better see how it all works, the best way is just going to illustrate with an example. So let's erase all of this. And let's say that here we have this matrix, and we want to see, can we diagonalize it? The first thing we have to do is find out its eigenvalues and its corresponding eigenvectors. And now we're going to proceed just as we did in videos 15 and 16. We say, well, we have to form this new matrix like this. Or actually, let's say this. This is our matrix here, and we want to find its eigenvalues and eigenvectors. This. And the way you get that is you take our original matrix and subtract lambda from the diagonal elements, just as we did in the two preceding videos. And then this new matrix that we get times the eigenvector that we're looking for equals the 0 vector. So in other words, the eigenvector for our original matrix lies in the null space of this matrix. And as we discussed before, that means then that this matrix must be singular, therefore its determinant must be 0. So we can find the determinant for this, set it equal to 0, then we can solve for lambda. So the determinant will be this times this minus this times this. So we have 2 minus lambda times minus 5 minus lambda. This times this minus this product minus negative 6 equals 0. Okay, and let's see what this gives us. Here we will have minus 10, and this will give us plus 5 lambda minus 2 lambda. That's plus 3 times lambda. Then from here we'll have plus lambda squared plus 6 equals 0. So let's see, we have lambda squared plus 3 lambda minus 4 equals 0. And let's see, we should be able to handle this pretty easily. Two numbers multiplied together have to give us 4, and added together have to give, or negative 4, and added together have to be plus 3. What if it was lambda, I think plus 4, times lambda minus 1? Does that work? Lambda squared plus 4 lambda minus lambda is plus 3 lambda minus 4 equals 0. Okay, so lambda is going to equal negative 4 and plus 1. Lambda equals plus 1 and negative 4. Okay. So here, lambda equals negative 4. Let's work with that first. So we have 2 minus negative 4. That should be 2 plus 4 is 6. This is 2. This is minus 3. And here we have minus 5 minus lambda. That would be minus 5 plus 4. That would be minus 1. So this times this equals 0. And these equations are pretty trivial, but let's just go ahead and write the augmented matrix. So we will have 6, 2, minus 3, minus 1, like this. And again, this column here would be the coefficients of x1 if we had this written out as two separate equations. We'd have 6 times x1 minus 3 times x2 plus 2 times x1 minus 1 times x2 equals 0. So these just correspond to those coefficients of x1, and these correspond to those coefficients of x2. And again, this is pretty trivial, but let's just go ahead and get this in row echelon form. We can exchange these two rows. So we have 2 minus 1, 0, and 6 minus 3, 0. Multiply this by minus 3 to give a minus 6. We add to make that 0. So let's do that. This stays unchanged, of course. So this is 0. And minus 3 times minus 1 is plus 3. Add to that. This is 0. So we end up with this. All right, but let's look at this. What is the lead variable and what is the free variable? Obviously, x1 is the lead variable and x2 is the free variable. So x1 lead, x2 is the free variable, and what we do is we want to express the lead variable in terms of the free variable, which is pretty easy to do. We have 2 times x1 minus x2 equals 0, so we're going to have 2 times x1 equals positive x2, or x1 equals 1/2 times x2. So our eigenvector here has components x2, that's the free variable, that can be anything, and x1, which is 1/2 times x2. So there's our eigenvector, and we can write this as, make some space here, this would equal x2 times 1 times 1/2. Or, again, this is our eigenvector. This can be any value we want it to. So if we want, this can be 2. Or the way we can think of it is, when you have an eigenvector, you can multiply it by any constant, and you still have an eigenvector. So this we could say is just simply 1, 2. That would be the corresponding eigenvector. So for lambda equal minus 4, the corresponding eigenvector is 1, 2. Now what we have to do is find out what is the eigenvector corresponding to lambda equal 1. When we do that, we'll have the 2 eigenvectors. Then we can construct the S matrix. Then we have to take its inverse. So I'm not going to have time to do that in this video. So come back, join us in the next video. We'll pick up where we left off. We're going to work with lambda 1 now. Put 1 here, put 1 here, solve for x1 and x2, and get the next eigenvector. So come back, join us for the next video. We'll pick up from this spot here, and we should be able to get this problem finished off.